Hello students and welcome back to this channel. So in this video we are going to be finalizing applied organic chemistry. So this video is presented to you by Ogimbe Yusuf, and you advise subscribe to the channel and share the video to your colleagues as well so that you can all pass as a team. So in this video we are going to be handling polymerization together with plastics, and for any inquiry you put your inquiry in the comment section. So starting, we are going to kick off with polymers together with polymerization. Now a polymer is just a substance. Polymerization is the process of making the polymers. So we're going to kick off by saying that a polymer is a large molecular mass compound that is going to be formed by repeatedly joining together small molecular units called monomers. So the monomers are going to be connected to each other in numerous amounts by covalent bonds so that you can form the polymers. So looking at the process of forming polymers is going to be called polymerization. And with this we are going to say that polymerization is going to be that process by which small molecules are going to repeatedly join together by covalent bonds to form a large molecular mass compound. So polymerization, I repeat, is the process of making polymers, but you can't define it that way. You define it as a process of monomers repeatedly joining to each other using covalent bonds to form a large molecular mass compound. So proceeding, we are going to say that there are two fundamental processes of forming polymers, or there are two types of polymerization, and one of them is going to be addition polymerization together with condensation polymerization. But in this case, many of you mess the first option up and then you go into losing marks. Addition polymerization, there's a difference between additional there's a difference between additional and addition polymerization. So majority of the students in exams, you present this one, and this one you do not qualify for any mark. So therefore, your answer will be rejected. So there are two, and the first one you should take a key emphasis on it. It's addition, it's not additional. So addition polymerization together with condensation polymerization are the only types of polymerization we have in forming polymers. So you're going to break down one by one, and you're going to start with the addition polymerization. So addition polymerization by definition is going to be the type of polymerization in which very many molecules of an unsaturated monomer. Note that here in addition polymerization, the monomers that we are going to use must be unsaturated. This is the key and very important note to summarize under this subtopic. So with addition polymerization, we are dealing with an unsaturated monomers. So it's a type of polymerization in which very many molecules of an unsaturated monomer join to form a large molecular compound, which has the same empirical formula as the monomer without loss of any molecules. So what you have to note here is that in addition polymerization, we are joining repeatedly unsaturated monomers, which have the same empirical formula to form a large molecular compound, which has the same empirical formula like the monomer. But in this case, in addition polymerization, we do not lose any molecules. When you cross to condensation polymerization, you see that the process is going to involve loss of some molecules such as water. I hope you have looked at condensation reactions in biology. So let's go ahead and look at the examples of addition polymers. So with this, one is going to be polyethylene, polyphenylethene. I hope you are seeing how I'm writing these monomers or these polymers. The organic compound or the monomer must be in brackets, and then poly is to indicate that there are very many of them. So here we joined very many propene molecules to get a monomer called polypropene. Same applies to polyethylene, polychloroethylene, which is the same as polyvinyl chloride. Now this is a very common polymer as during examinations together with polystyrene. So we can also look at natural rubber together with olon, and they are going to break down one by one. Now starting with polyethylene, here note that in addition polymerization, the monomer is going to have the same empirical formula like the polymer. So if at all it's polyethylene, you can see that our polymer is having an empirical formula of CH2CH2, just like ethene. Then this N here is the one which is showing that this is going to be a polymer, together with these hyphens that are going to be attached on either sides. So here we are going to say that polyethylene is also called polyethylene. But mainly this is the far better naming to use. So its monomer is ethene, which is written by a molecular formula of that, or a structural formula of that. And then the polymer has the following structure. So the polymer and the monomer, you'll find that they are having the same empirical formula. It's just that the polymer is differing from the monomer by the hyphens that are aside it together with the N that is a subscript of the empirical formula. So that's how you are going to identify addition polymers or compounds that have been formed by addition polymerization. So now looking at polyethylene, it's going to be divided into two, but we are going to look at one. We have low density polyethylene, we also have high density polyethylene. So in this, we are going to say that under low density polyethylene, this is a type of this type has a softening point of about 120 degrees Celsius, and it's going to be formed by compressing ethene molecules at high pressure and a temperature of 200 degrees Celsius using small amounts of oxygen. However, this is just a background. Mainly, we are not going to ask you about the description, but we may ask you to categorize polyethylene into two categories. So it's up to you to tell us that the monomer or the polymer given above, let me say in part B, is categorized into two. You say that one of them is going to be low density polyethylene and the other one is going to be high density polyethylene. So with that, we are going to make a simple equation that is going to show how our polyethylene is made, or an equation showing manufacture of polyethylene using ethene as the monomer. So N molecules showing that undefined number of ethene molecules combined together repeatedly at a pressure of 1500 atmospheres and at a temperature of 200 degrees Celsius using the oxygen initiator. But we say that oxygen must be in low supply, and then we form a monomer which has the same empirical formula. We form a polymer which has the same empirical formula like the monomer, and this polymer you have formed, note that it starts and ends with hyphens, and then N as a subscript to show that it's a number of molecules that have joined to form such a large molecular compound. So here, what you should note when you're writing this equation, or when you're given this equation, is that for addition polymerization, because when you're given the equation, we are going to ask you for the type of polymerization that has taken place. So what you should note here is that if at all you see any other compound being given off, that's not addition polymerization, because for addition polymerization, no other product must be formed. And secondly, for addition polymerization, the monomer is going to have the same empirical formula like the polymer. If you look at the monomer, we are having CH2CH2. And if you also look at the polymer, we are having CH2CH2. That also confirms addition polymerization. Now, usually in part C, we are going to ask you about the use of the polymer you have named above, or the polymer that has been manufactured in the equation. So one of the functions of polyethylene, it can be used to make plastic bags. For example, these white bags that you usually buy for shopping, you will notice that this thing is written there, polyethylene. So it's used in making plastic bags. It's also used in making toys, since it can be used as a plastic. It is also used in covering of cables because it's a poor conductor of electricity. It can also be used as a film for packaging and coating of materials. So after having looked at that, let's proceed to the next addition polymer, and we are going to look at polypropene. So polypropene is going to be attained by repeated joining of the monomers of propene, and this is going to be a high tensile strength material, and therefore it can be used in making tough materials such as tough fibers and ropes. So you're going to say that polypropene can be used in place of polyethylene. Therefore, that means that the advantages or the uses of polyethylene can be the same as the uses of polypropene, and this is what makes applied organic chemistry easy. So due to the advantages it has over polyethylene, for it is lighter and also it's tougher, and therefore it has a very high melting point as compared to polyethylene. Now let's just look at the details of polypropene. So here we are going to say that polypropene is going to be made by propene under pressure as a result of repeated joining of the propene molecules, but this is going to be done under certain conditions. Now usually as a student you are not required to cram this equation. It is just, mainly we are just going to bring for you these equations, and then we tell you to name the type of polymerization taking place. We tell you to name the polymer that is being formed. We also tell you to give the uses of the polymer that is being formed, and also the disadvantages of such a polymer it may have in the environment. I hope you have seen that it is used in making plastic bags, so therefore that means that some of the negative impacts that polymer has against the environment may be environmental pollution and also reducing soil tooth, also causing soil infertility, since polyethylene bags reduce water infiltration into the soil. So with that, let's first look at this equation. So according to the equation, you can see that the monomer is having the same empirical formula like the polymer. So this means that this is going to be addition polymerization. The conditions must be heat must be supplied, which is about 100 degrees Celsius, and then a low pressure of about 10 atmospheres. Then these ones are going to be catalysts to facilitate the reaction. At the end, you must have hyphens, and as a subscript, you must have a letter N. So with this, we can look at the uses of polypropene, but we say that they are going to be the same as those of polyethylene. They almost function the same way. So since it's tougher, it can be used in making ropes, carpets together with bottles. It can also be used in making packaging materials such as plastic bags, just like we looked at the advantages or uses of polyethylene. So proceeding to item 3, we are going to look at polyphenylethene. So polyphenylethene is also called polystyrene or polystyrene. So this one is mainly examined by mock bodies. But like I said, the advantage of these mainly equations are going to be presented. It's your duty to look to identify whether it's going to be addition polymerization or condensation polymerization. That you should note straight away from this video even before it ends. You need to identify whether you are dealing with addition polymerization, or you are forming an addition polymer, or you are forming a condensation polymer. You need to understand that from the beginning. So looking at polystyrene, we are going to say that is free radical polymerization, and it's going to be done using dibenzoyl peroxide as the initiator at a temperature of 85 to 100 degrees Celsius. Now if you look at this dibenzoyl peroxide, if you are to look at it back in organic chemistry synthesis, this is the reagent that can convert an alkane. It's the reagent that we use to convert an alkane into an alkyl halide. Is the only reagent acceptable in synthesis, if at all you are proceeding with the reactions, other than ultraviolet light. So you put more emphasis on that, or you ask for more clarity in the comment section. So looking at the equation of formation of polyphenylethene, note that this is going to be our monomer. Our monomer is called phenylethene. Phenyl is because of this alkyl group, which is for the benzene ring. An alkyl group for the benzene ring, we call it phenyl. And then we name it according to the compound attached. So it is attached to ethene. So alkyl group phenyl then the compound to which it is attached is ethene, so it becomes phenylethene. So if we get a bunch of phenyl molecules, so I forgot to put in here, you make sure that you add that in there. So if you get a bunch of phenylethene molecules and then you combine them repeatedly under conditions of dibenzoyl peroxide as the initiator and between a temperature of 85 to 100 degrees Celsius, you're going to get polyphenyl ethene, and this is going to be the formula. So what happens is that the double, I don't know whether you're recognizing, is that this double bond during formation of the polymer is going to scatter on either side. So this one of these bonds gives off a bond there, it also forms a bond there. But notice that here, many students make a mistake and you put this bracket onto this whole benzene ring, which is very wrong. This bracket must be only on the ethene group. Do not make sure that the bracket does not reach the benzene ring. So you bracket the ethene group and then you put hyphens on either sides. You also eliminate the double bond and then you put N as a subscript of that bracket. So since the polymer is having the same empirical formula like the monomer, this one is going to confirm that this is going to be addition polymerization. Now let's look at the uses of polyphenylethene. So one of them is going to be making thermal and electrical insulators, since they are poor conductors of heat and electricity. Also, we are going to be using it in making lightweight packaging materials. We can use it in making household items such as egg boxes, where you put eggs. And also, we can be using it to make lining of materials such as refrigerators, and also making theatrical properties. And also it can be used in decorative purposes. They use mainly plastics and polymer materials in decorating weddings. So after you're graduating at university, make sure that you apply some of these items that you're studying using the knowledge of chemistry. So now looking at the other item, we are going to look at polyvinyl chloride. Like I said, this is also very common, especially this is mainly said by UNEB examination bodies. So polyvinyl chloride is also called polychloroethane. So polychloroethane is going to be formed simply by heating chloroethane in an inert solvent with dibenzoyl peroxide as the initiator during this polymerization. So what we do is that we get molecules of chloroethane. Chloroethane is going to be written in this format. So the N is showing you that we are combining a number of molecules of chloroethane. So the conditions are going to be dibenzoyl peroxide, and then you apply some kind of heat. Then what happens is that one of these bonds will form a bracket, and then one of these bond scatters and forms hyphens on either side. That's why we end up with this product. After that, you put N as a subscript down the bracket. So this is what is called polyvinyl chloride. Now this one is commonly asked in line or in relation with osmotic pressure. After you calculating for the molecular mass of a polymer, we tell you that that polymer was polyvinyl chloride, and then we ask you for the number of monomers. So for you to do that, you need to first understand the formula of polyvinyl chloride. I hope that is clear. This is very, very important. So if you're taking your notes, make sure that you put a styrific note on it. You need to understand this, and I'm sure that you have come across such questions because it's a very common question. Under osmotic pressure, we always link osmotic pressure to this polymer here, polyvinyl chloride, since we use it mainly in experiments. So here, polyvinyl chloride is a very tough polymer, and therefore we can use a plasticizer usually to soften it so that we can make different products that we can use so that it can be beneficial to us. So it is also resistant to weathering, fire, and chemicals, and therefore it can be used as a good electrical insulator. Now let's see some of the uses under which we can use polyvinyl chloride. So one of them can be used in manufacturing of raincoats, curtains, together with furniture coverings. Also water piping and guttering. We can also use it as insulators of cables, and also we can use it in manufacture of artificial leather. We can also use it in manufacture of gramophone records, among others. The good thing with polymers, you can give any advantage where you have seen a plastic being used, or where you have seen anything which is a poor conductor of heat being used, because polymers mainly are poor conductors of heat. Now let's add on some bit of revision about other adhesion polymers. So in this, we are going to go through this one quickly. So this one is also called passports. So sometimes also mock bodies try to present this one, and to identify it, I've told you that you look whether the molecular formula the empirical formula of the monomer is the same as that of the polymer, or is the conditions we are going to use in preparation of majority of these reagents is going to be heat plus a catalyst or an initiator, and the initiator that we use is going to be dibenzoyl peroxide. To identify whether it's addition polymer, it's an addition polymer being formed, you look at the empirical formula of the monomer and also that of the polymer. And to identify the polymer that's going to be formed, you simply take I1 bond from here, and then you give this product two brackets, you form hyphens across it, and then you put N as a subscript, and then that's how you get your polymer. I hope you have understood that. Alright. So perspex, since it's light and strong and also transparent and plastic in nature, it can have a variety of uses, and some of them are going to include the following. So one, we can use it in packaging, and the other way we can use it in making of airplane windows, lenses together with corrugated roof lights, which are mainly on vehicles. So another one example of addition polymer is going to be Olan. So the initiator here is going to be peroxide initiator, and it's going to form this polymer. So you can see that you just remove one bond, you form brackets, and then you put hyphens on either sides, and then you put N as a subscript. You always notice that in addition polymerization, the monomer and the polymer are going to have the same empirical formulas. It's just that the polymer does not have the double bond, whereby one of the bonds forms hyphens on either sides of the bracket on the polymer, and then you put a subscript of N to show that we added numerous number of monomers. So proceeding, we are going to see that the polymer is used in making clothes, blankets, and carpets. So we look at another addition polymer, which is going to be rubber. Now rubber, we are going to look at it in details because rubber consists of two forms, or it can be categorized into two. So one is going to be natural rubber, and the other one is going to be synthetic or artificial rubber. So synthetic is the same as artificial. But usually here we get some questions that are easy to understand and easy to pass, but quite tricky to interpret. So rubber, types of rubber or forms in which rubber is categorized is natural together with synthetic. So we have natural rubber and synthetic rubber. So starting, let's have a brief outlook on natural rubber. So rubber is obtained from latex, which is an emulsion of rubber particles in water found in the bark of many tropical and subtropical trees. Now people living in either eastern region of Uganda or the western, people grow pines. I hope you have seen some industries or some people extracting rubber out of those trees. So we get them from the bark of the tree. The bark of the tree is that tree coating, whereby we get some pipe and then we insert into that bark, and then rubber, which is unprocessed, starts flowing out, and then it's collected in a separate container, which is later taken to the industries for processing, so that you can get or we can obtain that natural rubber. So here we are saying that the latex extrudes from the bark. Now this latex is what we call the unprocessed rubber. So it extrudes from the bark of the tree after it's being cut, and then raw rubber is coagulated by adding ethanoic acid. I hope you have understood that. So proceeding, we're going to say that natural rubber is also going to be called polyisopropene, and is a polymer of the monomer whose opaque name is going to be called. Now here, you don't need to overcram this name because I've told you here, mainly we are going to provide you with the equations. We are going to provide you with the equations and we ask you which type of polymerization uses of that polymer. Name. We may also ask you to name in case we see that it's going to be simple. For example, this polymer can easily be named, but don't put much emphasis on cramming equations. So here the initiator or the monomer is going to be called isoprene. That's why the polymer is called polyisoprene. So you can either say isoprene or polyisoprene as the monomer or polymer respectively. So when you use the Gila catalyst, we are going to be forming our rubber, which is also called poly-2-methylbutan-1,3-diene. So proceeding, we are going to say that natural rubber is not strong enough and not elastic enough material for use, and therefore it softens and becomes sticky on heating. So with this, on cooling, it's going to become hard and brittle. So these problems can be largely solved by a process which is going to be called vulcanization. Now here we can form a question that rubber after being extracted is hard and brittle. How can we overcome such a scenario? Like, we have very many ways of setting vulcanization. Mainly we used to say this at ordinary level, but mainly we are also trying to bring it or to engage it in mocks. So you need to understand the process of processing rubber and the process of processing rubber into a desirable commodity which can be purchased from the market is through vulcanization. That's how we are going to process rubber and to be ready for proper usage. Let's look at the process of vulcanization. So under this, we are going to say that vulcanization of rubber, raw rubber is going to be heated up to 8% sulfur. And then the sulfur is going to form cross linkages between the neighboring polymeric chains of rubber. Then accelerators of vulcanization are going to be used so as to increase the rate of combination and to allow the process to take place at a lower temperature. So here what you should note here is that we are heating our rubber with sulfur, 8% of sulfur, and the purpose of this sulfur is to form close linkages between the neighboring polymeric chains of rubber. So what you should note here is that we may ask you, during vulcanization process, sulfur is used. Give or examine the importance of sulfur in the vulcanization of rubber. So its main function is to form close linkages between the neighboring polymeric chains. And then we add accelerators of vulcanization to increase the rate of combination and to allow the process to take place at a much lower temperature so that energy is not wasted. So the accelerators that we may use, they may either be organic or inorganic, and this is not that important. So vulcanized rubber is better to use than natural rubber because of the following. One is going to be more durable and the other is going to be more elastic, and the other one is going to have a greater tensile strength. Remember that we are vulcanizing rubber to put it into a desirable commodity. So when you are giving functions of vulcanization of rubber, you should give advantages or importances of processed commodities over unprocessed commodities. So one is going to be more durable than the unprocessed rubber, and it's going to be more elastic than the unprocessed rubber, and it's also going to have a great tensile strength as compared to the unvulcanized rubber. Now let's look at artificial or synthetic rubber. Synthetic is the same as artificial. I hope you know that all the way from your O level. So looking at synthetic rubber, we are going to say that for synthetic rubber, it's also going to be called neoprene. And this polymer, whose opaque name is going to be poly-2-chlorobutan-1,3-diene. It's going to be made from a monomer which is going to be 2-chlorobutan-1,3-diene. So looking at this, we are going to say that it's more expensive to produce as compared to natural rubber. Since it's artificial, we need to engage in a lot of raw materials in its processing. So during polymerization, potassium persulfate is going to be used as a catalyst. However, I didn't go deep into the synthetic rubber manufacture since for it we are no longer examining it. We focus mainly, if we are to bring rubber, the main focus is going to be, if you're to bring rubber, the main focus is going to be on vulcanization, also category, natural and artificial, and then purposes of or importances or uses of vulcanizing rubber, and also maybe we may push in some bit of talking about the process of vulcanization. Now let's look at the importances or the main importances of rubber or uses of rubber. So one you're going to look at making coverings of underwater cables, making golf balls, making car tires, making shoe soles, and then making waterproof boots together with making hoses and gaskets, among others. You give anything or any use of rubber, any material that you have seen being made in rubber. It may be a pencil, it may be a car tire, it may be a wheelbarrow tire. You give all the uses. I say that applied chemistry is very easy because they're asking you chemistry which you already see in your daily life. So that was it with addition polymerization. So proceeding, we are going to be looking at condensation polymerization. Now, unlike addition polymerization, in this polymerization, you are going to be losing some molecules. Condensation, you are going mainly is going to be water molecules. After forming our polymer, we are going to lose a certain amount of water molecules. So this we are going to say that under condensation polymerization is going to be the type of polymerization in very many molecules of two different bifunctional monomers joined together to form a large molecular mass compound with loss of some molecules such as water, ammonia, methanol, carbon dioxide, among others. But in your definition, all you have to do is that when the monomers that are going to be combined, they have to be having different functional groups. That's why we say bifunctional monomers. And secondly, there must be loss of a molecule or loss of small molecules such as water or ammonia or methanol after such a polymer is formed. So make sure that in your definition, you're having bifunctional monomers as the key term, because the two monomers you are combining or the monomers that you are combining must have different functional groups. And also, after forming your polymer or the large molecular mass compound, you must form it with lots of small molecules. For example, water, ammonia, ethanol, or carbon dioxide. Now looking at the polymers that are formed by condensation polymerization, we are going to look at nylon 6 to 6 and also nylon 6 to 10. We also look at melamine. Melamine is very common. It's what you use in manufacture of your plates. I hope you have some plates of melamine at home. If you do, you can like this video. We can also look at proteins. Now, mainly biology students, you know very well that majority of the biological components, lipids, whatever, carbohydrates, majority of them combine through condensation reactions, leading to loss of water molecules. We can also look at the silicones together with the wool. So trying to break through one of them. Now these are the equations which you should just look and identify whether it's addition polymerization or condensation polymerization. Always in the examinations, the equations are going to be given. So don't bother yourself in trying to cram either the name or the equation. What you should note maybe is to see how compounds or the polymers are going to be formed. You should be very conversant with that. So when you're forming terylene, which is also called fortryl, is going to be a polyester that is going to be formed by interaction between bifunctional monomers. One of them is going to be dicarboxylic acid and the other one is going to be a diol. So it's going to be formed by two monomers. One of them is going to be this, which is benzene 1,4 dicarboxylic acid, and the other one is going to be ethane 1,2 diol. So when ethane 1,2 diol combine with benzene 1,4 dicarboxylic acid, the following equation is going to be the result of the formation of the polymer. So if you look here, I want you to pay attention closely here during formation of these polymers, because this is where you are going to get everything mixed up. So note that here in this condensation polymerization we are losing water molecules. So you should put your emphasis there. We are going to lose water molecules. Now since these ones are having two functional groups, that means that we are going to be losing two water molecules when these two combine. So one water molecule is going to come as a result of the carboxyl group is going to donate the OH group. And then we also pick one hydrogen atom from this. We pick one hydrogen atom from this ethane 1,2-diol. So when these two combine, we are going to form the first water molecule. I hope you have understood that. So after forming the first, when these two combine, this CO group is going to attach to the remaining compound. So the remaining compound, you see that this is the CO group, and attaching to this remaining compound, which is going to be OCH2CH2, then OH. But here you're not seeing the H. So what happens is that also this H here comes and combines with the remaining OH group on the other side of the benzene ring. And when it does so, we also lose the second water molecule. So after losing this H at the end, is that we leave an hyphen, and we also leave an hyphen this side for losing the OH group. And then we give it a bracket, and then we put a subscript N at the end. I hope that has been clear. Here we are losing two water molecules. All your focus should be is that the carboxylic group loses the OH, but this diol loses the H group. So first, this OH on the carboxyl group goes with that, and then this compound joins to the CO, and then you form this side of the polymer. And then this OH group which is left here combines with the OH group which is left on the other function, on the other carboxyl group on the benzene ring, and then we lose another water molecule. And then this time round, the bonds that have been holding the H form a knife in this side, and also that have been holding the OH form a knife in this side. We put our polymer in the brackets, and then we put a subscript of N beneath it. And this one is also, this is what we call a condensation polymerization reaction, a condensation polymer, because we have formed a polymer and we have also lost a water molecule. In addition, polymerization, we do not lose a water, or we do not lose any molecule, but here in condensation polymerization we lose molecules such as water, mainly water, and ammonia, or it may be methanol. So we are saying that here, for this reaction to be effective, an acid catalyst must be used for the reaction to take place, and water molecules are used. That's why mainly they are called condensation reactions. So they're telling you that instead of benzene 1,4-dicarboxylic acid, benzene 1,4-diol dichloride can also be used instead, and together with ethane 1,2-diol. And let's see the equation for that. So with this equation, also the mechanism of joining this polymer, or forming this polymer, is going to be the same. So this chloride joins with the first hydrogen atom here, and then we form hydrogen, we lose one hydrogen chloride molecule. So this other product attaches to the CO group. That's why you saw this. Also this hydrogen atom comes and takes away the chloride which is attached here, so that we remain with hanging bonds. So the hanging bonds are the hyphens that you see on either sides of our polymer, and then we bracket our polymer, and then we give it a subscript of N. So you're saying that in this reaction, no catalyst is going to be required. Also, molecules of hydrogen chloride are going to be lost instead of water. So since we are losing molecules, or we are losing small molecules, it's going to be called a condensation reaction. This is going to be called a condensation polymer. I hope you have seen that formation of these compounds is not that complicated, like the way you see them when you handle them personally. Or your teachers may use another technique in teaching you. Some of your teachers don't teach this topic, they just give you notes. So you're saying that in this reaction, no catalyst is required, and therefore molecules of hydrogen chloride are going to be lost. So since we lose molecules of hydrogen chloride, this reaction or the formation of this polymer qualifies to be under the process of condensation polymerization. So use dissolved polyester, which is also called toluene. We can use it in making clothes, making ropes, together in making safety belts. Now you can also look at nylon 626 as another example of condensation polymerization. So nylon belongs to the class of polymers called polyamides, though this one is not that necessary. So nylon 626 is called so because it is formed by two monomers, each of which has 6 carbon atoms. So one of them is going to be hexane 16 diamine, which is represented by this formula, and the other one is going to be hexane 16 dioic acid. So you can see that in condensation polymerization, all the monomers that are used, they are having different functional groups. So the equation for combination of those elements is also going to be the same. So anytime you see a carboxyl group, you notice that this carboxyl group is going to donate always the OH group. So the other monomer is going to donate only the H atom. So this H atom picks up this OH group, and then we form this side of the chain. And then this H group goes with the OH group on the other side of the carboxyl group, and then we leave hanging bonds. So these hanging bonds are what forms the bonds that we need to put in the bracket to indicate that we have formed our polymer. And then we put the N beneath, showing that we have combined a bunch of them to get this polymer. So since we lose water molecules, this is going to indicate that this is going to be a condensation polymerization. So also hexane 16 dioil dichloride can also be used instead of the dioic acid, and they're going to combine in the same format. So the chloride is going to go with one hydrogen atom, and also this hydrogen atom is going to go with the one chloride, and then we lose hydrogen chloride, and that's how we form polymers. I hope you have learned how to form the polymers, both addition polymers and condensation polymers. And if you have done, make sure that you like this video. And for any areas of concerns, make sure that you leave your concerns in the comment section, though we made a WhatsApp group for that. So in this case, hydrogen chloride is eliminated instead of water, and therefore that one is a condensation polymerization reaction. So nylon 626 is greatly versatile, and some of its uses are going to include the following. One of them is going to be used in forming fishing nets, bottles, ropes together with clothing. It can also be used in making structures such as gears and lubricated bearings together with tarpaulins. Now with that, let's look at the differences that can exist between addition polymerization and condensation polymerization. Now I hope you have already noticed these differences. So what you're going to do here is to highlight or to make them more prominent. So addition polymerization is going to involve one type of a monomer. We have seen that in condensation polymerization is going to involve more than one monomer, or it's going to involve two types of different monomers. Also, in addition polymerization, all atoms of the monomer form part of the polymer. That means that there is no atom which is lost. Whereas in condensation polymerization, some of the monomers or some of the atoms from the monomer are going to be lost in form of small molecules. Also, in addition polymerization, you notice that the empirical formula of our monomer is the same as that of the polymer. But in condensation polymerization, the empirical formula of the monomers or the constituent monomers is very different from the empirical formula of the polymer. Also, in addition polymerization, we notice that monomers usually contain at least a carbon double bond. But in condensation polymerization, we have not noticed any carbon-to-carbon double bond. So addition polymerization involves monomers which contain double bonds of carbon as opposed to condensation polymerization. Also, when you look at addition polymerization, is that the molecular weight of a polymer in addition polymerization is going to be an integral multiple of the molecular weight of the monomer. But in condensation polymerization, the molecular weight of your polymer is not an integral multiple of the molecular weight of any of the monomers you have used. Now proceeding, we are going to also look at plastics. Now plastics are mainly polymers. So this one is going to be just a finalizing part of the polymerization and applied organic chemistry at large. Now under plastics, you have what you call this thermosoftening plastics together with some thermosetting plastics. And let's look at each of them. So when you start with thermosoftening plastics, these are also called thermoplastics. So these are the plastics which can become soft when heated, hence can be remolded. So thermosoftening, just like the name suggests, thermosoftening, when you heat them, they can soften and you can easily reshape or remold them. So these thermoplastics easily soften on heating because they consist of long polymer chains which are usually held by weak intermolecular forces of attraction. And these weak intermolecular forces of attraction only require small changes in temperature to overcome, and therefore that's why they easily become soft when small amounts of heat are applied. And some examples of them, we are going to look at polyethylene, polyvinyl chloride, polypropylene together with perspex. But also we are having also what you call the thermosetting plastics. Now these are plastics that are going to have a three-dimensional network of bonds which are very strong, and therefore for them they cannot soften during heating. A good example of this are going to be melamine plates. If you heat those plates, you find that such kind of plastic, it cannot be remolded because for it, the forces holding the polymers in it are very strong, in that when you heat it to the maximum temperature, it can't be remolded or it can't soften, but it just perishes away. So we're going to talk about this as plastics which contain three-dimensional network of bonds and are molded during the polymerization stage of their manufacture, and they cannot be softened or remolded on heating. So these polymers are going to require very strong heating to bring about any form of chemical change, and the reason for that is because they are joined by strong forces of attraction held by strong covalent bonds. So examples of thermosets or plastics that cannot be remolded on heating, or that do not soften on heating. One of them is going to be bakelite, the other is going to be melamine. We also have vulcanized rubber together with expoxylenes. Looking at the differences because we usually examine this when we give a question about plastics. Give a difference between thermoplastics together with thermosets. Sets or thermosets, they do not soften on heating, you should know that. And also their polymers are joined by strong forces of attraction, unlike the thermoplastics. So the difference is thermoplastics have low melting point, whereas thermosets have a very high melting point due to the variance in the magnitude of the forces holding either of them. So thermoplastics usually soften on heating and therefore can be reshaped or remolded, but thermosets do not easily soften on heating, or simply can say that they don't soften on heating and therefore they cannot be reshaped or remolded. So another difference under thermosets or thermoplastics, you find that thermoplastics are held by weak van der Waals forces of attraction. These are the forces that enable them to be remolded on slight heating. But these thermosets are held by very strong covalent bonds to the extent that for them even to reach their melting point or boiling point, you have to first heat them at a very high temperature due to the strong covalent bonds holding their monomers. And thermoplastics also have linear polymeric chains, but thermosets, their polymeric chains are close-linked. Thermoplastics also can be recycled since they can be reshaped and remodeled, but thermosets, they cannot be recycled. There is no way you can recycle a melamine plate, but other plates may be recycled. And also thermoplastics are soft and flexible in nature as compared to thermosets that are hard and brittle in nature. Now lastly, let's look at the effects or some of the effects of plastics on our environment. So plastics being non-biodegradable, their poor disposal in the environment is going to lead to environmental pollution, as earlier mentioned about this. So some plastics are burnt and they form toxic gases which may lead, such as hydrogen chloride, and these ones may lead to air pollution and also killing of some microorganisms that may be found in air and leading to depletion of oxygen or causing global warming. But these problems can most effectively be overcome through recycling of the products unless or excluding the thermosets which cannot be recycled. But majority of the plastics that we use are thermoplastics which can be recycled. So this is it for this video under applied organic chemistry. So this video was concluding applied organic chemistry. The next video is going to be about amines. Now you help and share the video to your friends. Help your colleagues as well to excel just like you found the blessing of getting onto this channel.